Hey, welcome back. How's everybody doing? We'll woken up a little bit. I won't ask you to do more number games. Maybe more interesting stories instead. All right, welcome back. So like I mentioned a little bit earlier, part one is where the vast majority of methodological literature rests on, that were sort of started in 1970s when this cottage industry sort of started to develop, also in epidemiology and biostatistics. I put them in the sort of the school, the island of earlier population research or early investigations. So starting with this part two, we move on to a more recent development, which I think is starting to give us something more to chew on in terms of its utility. Whereas the first part focuses on counting. It's an accounting game. We're just describing what's how the outcome is allocated, attributed to these three different dimensions of time, related changes. Part two starts to take off and look into something deeper. So that's where, I as a sociologist start to become a little bit more excited using this kind of new ways of looking at the data that can help me do more things. So this part is about hierarchical models applied to APC analysis. So I put them together as hierarchical APC or HAPC models for research design 2. What is research design 2? So, well, we'll get that later. First, I would like to begin by reflections of some major limitations of linear models that we just looked at. And then, in light of this discussion, I introduced a new design and talk about its new structure and new opportunities and some examples. And then I will show this sort of alternative to linear, so hierarchical model specifications through the mixed effects models applied to the second research design with also examples and possibly some extensions to these examples for your reference in the future. Now, it is important to point out that the identification problem is not inevitable, counter to many used to believe. It is largely a function of the application of the linear model to the data in the form of the first research design. That's why I emphasize, research design and the model fit to this design. It is important to keep that in mind when we do this sort of exercise. So, and this problem is inevitable whenever two conditions are simultaneously met. First, A, P, and C variables are linearly related to each other. We already talked about that, P being equal to A plus C. And also, each variable is also postulated to be linearly related to Y. Now, the linear models dominated APC analysis for so long that researchers took them to be the only models that can be used and seldomly think about their problems, their deficiencies. So there's the confusion about the origin and nature of the problem, thinking that it is inherent in any APC analysis because the A, P, and C variables are always exactly linear. Well, in the first kind of design, right? So as a result, previous studies are almost exclusively focused on finding solutions to break condition 1, breaking the linear dependency of P, A, and C, while paying little attention to condition number 2. And so what I emphasize is that there should be a different kind of insight into this problem after we lay out this way, right? So this new insight then would be that the problem is not necessarily data specific, but rather model specific. And how you conceive their relationship with the outcome matters a lot. And so While the APC problem has always been conceived as a methodological problem, I argue that it is also a theoretical problem, because the linear model induces this problem by imposing a key assumption of additivity, right? So y is equal to a plus p plus c. So thus treating the three variables as fixed effects that are independent of each other, and the outcome is modeled as a function, of them, all these, effects independently as fixed effects. So, I think this is okay, but it's a simple approximation to the actual process underlying change, and may not actually always accurately describe a age, period, and cohort-related phenomena that we're interested in modeling. I argue that a new framework is needed to accommodate non-additive processes that can help to better characterize the cohort and period effects, and also, stimulate new conceptualizations of processes of change other than additive, effects, and therefore move us, toward the goal of, we could use this kind of analysis to address new theoretical questions. It's a tall order, but let's see whether we can move one step forward to it. So to move beyond the identification problem, we begin with better data. So the first research design also is repeated cross-sectional, but just at the population level, right? And so the second design uses also repeated cross-sectional, but they're from sample surveys. And so what these surveys can do is that they provide us micro data on individuals. So we can, for instance, rearrange the individual level observations into a cohort by period cross-classification. So here, in this example, we're cross-tabulating the data, individual level data by cohort J and period K. Right, so the key characteristic of this kind of data immediately are different from the first one, because you would have different varied interval lengths for the three variables. So age in surveys usually are measured in single years. P is usually defined by survey years, and C can be defined more flexibly, either demographically as before, such as 10-year groups, or it can be defined substantively by pop culture, such as baby boomers, Gen X, Gen Z, so on and so forth. So in any case, the interval lengths between these three variables are not identical, A and P, and so they don't immediately, what you would know is that this kind of breaks the linear dependency between the three variables. Now, what's more important is that this kind of data gives us multi-level observations. So we have individual level data nested within each surveys with individual characteristics, including age, their other attributes, sex, race, so on and so forth. And also, individual members of cross-classified, they're nested in and cross-classified by time periods of survey and cohort membership as to higher level contexts. So what this means is that individual members of any birth cohort can be interviewed in multiple replications of the survey, and individual respondents in any particular wave of the survey can be drawn from multiple birth cohorts. And hence the NJK, the sample size in the J by K cell, is larger than 1. And this is a clear difference from research design 1, where we emphasize the cell size. The sample size for each cell is 1 rate. Here you have multiple individuals in here, so which indicates multi-level data. Similar to the first research design, this design also gives us synthetic cohorts. And then, so these are the major characteristics. So as an example, we have NHANES data, National Health Nutrition Examination Surveys. In the example that I will give, I'm limited to age ranges 25 to 74 from 9 survey periods. So each survey spans a couple years, or they're unevenly conducted also, and they're still ongoing, but I stop at 2007. So here we have 17 5-year birth cohorts in the studies that I will show on obesity. And then here are some other sample characteristics. So this is the actual data that I will be using, the summary statistics, where we have the dependent variable being the measured BMI to determine the obesity status. And we have over 40,000 individual observations. Level 1 variable at the individual level, we have age in years, sex, race, SES, including education and family income. And at level 2, the higher level unit, we have birth cohort, it's 17 5-year birth cohorts and 9 survey year periods. So this clearly shows the multi-level structure of the data and the sample size at each level. Now, so the data structure is as such, it helps us understand where we could go in terms of getting new solutions to the linear models problem. So recalling the two conditions inducing the identification problem I just talked about. So first is the linear dependency between the 3 variables. The second is their relationship to y is linear, right? So recalling these two conditions. So we have multi-level data here that resolves condition 1. So the differential time interval lengths of the 3 variables breaks the linear dependency. While you can, computationally still do a linear models with no identification problem, but that doesn't really solve all the problems because we talked about other problems with linear models. And this differential grouping is a kind of constraint because it frees up the degrees of freedom that come with their own, limitations. So, but also when you have multi-level data, you have level 1 heterogeneity and level 2 heterogeneity. And the linear models don't deal with level 2 heterogeneity effectively, and it cannot be accounted for. And therefore, we need to specify new models to account for this problem. And so we use the mixed effects family of models, hierarchical models, and this can help us resolve condition 2 that contributes to the identification problem. Now, so the mixed effects models can overcome these problems by moving us beyond the problem by not assuming all 3 variables being linearly related to y. And we'll see the model specifications in the next slide to understand why that is the case. Just in case, how many, you are all relatively familiar with mixed effects models, I assume? Okay, just want to make sure. So conceptually, I would like to emphasize 2 breakthroughs of these new models and data compared to the first kind of model to the fit to the research design 1 is that first conceptualizations through the data and the model avoids the model identification problem is very kind of promising sort of development. And also what's even more exciting is that by incorporation directly in the models of additional covariates, right, either at the individual level or at the contextual level, can help us test mechanism-based hypothesis. And this is definitely a step up from the linear models where, if you recall the model y being equal to alpha plus beta plus gamma, it's even short of 1 degree of freedom with just these indicator variables. It has no room for adding covariates to test for, say differences across sex, race groups, and education as an example. So this moves us so much beyond the identification problem and allows us to do more interesting hypothesis testing. So we use the hierarchical linear models or alternatively mixed effects framework to do this. What this model does is that it modifies the linear model assumption of fixed effects to a more flexible, more general mixed effects modeling approach. And it can directly model and explain the multi-level heterogeneity in the data that linear models cannot do. Now, when fit to the cross-classified repeated sample survey data that I just showed before, there's a specific form that's called cross-classified random effects. Basically means the level 2 random effects are cross-classified with each other. It's a fancy name. So I just call it CCREM so I don't do tongue twisters every second of the day. So what this model does, it can help us assess the possibility that individuals in the same periods and this coming from the same birth cohorts could share on observed random variance and hence level 2 heterogeneity. And it can also very flexibly incorporate covariates to model the effects of individual level attributes as well as contextual characteristics of time periods and birth cohorts on the outcome. So, and therefore it can allow us to test explanatory hypotheses of A, P, and C effects not possible in linear models. Well, the linear models were also called accounting models. So it's accounting for, these three, but it does not explain why they may have the effects that you see. So I think this new frameworks can allow us to do that, which I think is highly desirable improvement. So my plan for the rest of this section is to introduce the basic model specifications on which we could build many other extensions. And I'll use the enhanced obesity data that I just showed as an example for this model fitting. And then I'll talk about two readily available, relatively straightforward extensions based on the basic model, moving from random intercept to a random coefficient model, continuing the obesity analysis. And then also another extension is to add level 2 or period and cohort level covariates using an example of the happiness data from a different data set. So beginning with the random intercept model, I separately write out level 1 and level 2 just to show the structure a little bit clearer. So at level 1 in this data structure, if you recall, we have individuals, right, within cell model where we specified the risk of obesity to be functions of fixed effects of individual level characteristics, including age, age square, sex, race, education, and income. And for individual I, that goes from 1 to njk, which is the maximum, the number of individuals within cohort J and period K, where J goes from 1 to 17 5-year birth cohorts, K goes from 1 to 9 survey years, right? So this is the level 1 model. At level 2, we call it between cell model, where level 2 is cross-classified cohort and period variable, right? So here, it's a random intercept. If you go back to equation 1, we have this intercept beta 0 jk. Okay, so level 2 model zooms in on this intercept, random intercept beta 0 jk to be written out in equation 2, where gamma 0, 0 is the adjusted mean. C0j is the cohort-specific random effect coefficient, meaning this equation is saying the intercept beta 0 jk is varying from cohort to cohort with the cohort level, with the cohort specific random effect coefficient C0j around the adjusted mean gamma 0, 0, and also is modeled to vary from period to period with the period specific random effect coefficient P0k around this adjusted mean gamma 0, 0, where the cohort random effect C0j and the period specific random effect coefficient P0k being both normally distributed with mean of 0 and variance of tau C for cohort random variance and tau P for period random variance. So C and P are random effect coefficient for each J and K, and tau C and tau P are random variances corresponding to cohort variation and period variation. So tau C and tau P are the variance components that we care about when we conduct statistical tests to determine whether period and cohort variation, cohort random variance are statistically significant or not. we the typical what's available in typical computational software is z-test. I will talk about an alternative test later in the extension as well. So this is the basic structure, and then of the level 1, level 2 model, and then what you do is to put them together. It's simple algebra of equation 3 is just put equation 1 and 2 together, and you write out the combined model here, where the first 2 rows are the fixed effects, age, sex, race, education, income, as they always were in equation 1. And the last component here is the random parts of the model, where we estimate the cohort effect and period effect. And I also provided the interpretation of if you combine the mean gamma 0 with the cohort random effect C0J, you get beta 0J, where that's cohort obesity effect averaged over all periods. Similarly, if you put intercept and period random effect P0K together, you get beta 0K, where that's that indicates period obesity effect averaged over all cohorts. So, and then you estimate a model, you get these numbers, you put them together, and then you have a story. So before I show the software, we'll talk briefly about model specification. This is also a typical thing to do when you estimate mixed effects model anyway. So it has to do with the centering or the location of the individual level variables. Sometimes also, level 2 variables as well. But let's here just talk about individual level. So especially when the variables are continuous. So there are 2 choices of kinds of centering. One is the grant mean centering, where and the choice between the grant mean centering and centering within subgroups such as cohort is a substantive one most of the time. In this example of obesity, we consider age effects of obesity reflecting the influence of physiology more than anything. It may not vary by context, such as cohorts, so we do the grant mean centering. And this is often the case, usually a sort of default to go for hierarchical linear model estimates anyway. So, and there are other continuous variables, if they're included, they should also be centered for ease of interpretation of the intercept. So with that said, this is a screenshot of something I did years ago, so forgive me if it's not very polished. Some sample codes using SAS. So the first step is that I did center the age variable in a mechanical way, but there are better ways to do centering with the codes. So after I fix that, I estimate the model using Glimix. In SAS, generalized mixed effects models, Glimix. Linear mixed models is just prog mixed. So here is the outcome is obesity, so it's kind of logit link, so I use Glimix. The model statement, basically, if you write out the equation, that's the basis for your model statement where you lay out all the fixed effects variables, distribution binary, and the random statement is where you specify the random effect. There are 2 ways of writing the random statement. One is the abbreviated way because it's a simple random intercept. I just put period and cohort directly in there. Alternatively, you can be more true to your equation to write out random intercept period, random intercept cohort, and they're the same. The solution part of the code requests the SAS to request the program to output the random effect coefficient for you. Just the same as the solution for the fixed effects part of the model, where it asks the model to output the fixed effects estimates for you. COV test is the requesting the statistical test for the random variance components. And then the default, algorithm for the for the computation is Newton-Raphson Ridge. There are other algorithms you can choose to specify. It's all completely sort of custom to what you would want to do. And then so alternatively, these are some sample codes from Stata on the left, where you use the mixed statement and specify the cross-classified random effects by the statement of all R and all R for period and cohort respectively, using the REML, which is also what SAS used, the restricted empirical-based likelihood estimator. And then the R sample codes is on the right. We'll use LMER to estimate this, and this is the codes for random cross-classified, effects part. So relatively straightforward if you have already used mixed effects before. So this is a screenshot of the SAS output. So what you should expect to see if you estimate the model. This is the top part of the model that describes, the general situation of the model information, the period and cohort variable, the number of observations, and the dependent variable coding. This is the sample fixed effects estimates part of the output of, all the variables we just talked about: age, sex, Black, education categories, income categories. So they're readily, transportable to a, typical journal article style table where you report the parameter coefficients and the test of significance. And so this part is the test of the random variance, components part, where at the bottom there's some small numbers here, but if you look at covariance parameter estimates, and so this is a little table where I put in here to correspond to our cohort random variance estimate, the z-test, which shows it's not statistically significant in this particular case, but for period, there's a sizable variance component, and that is statistically significant. And so this comes from this little box here in the output. And then, so when you request the solution, it prints out the actual random coefficient estimates for you. Here's a screenshot of just the top 4 of those for each period and cohort. There's the rest, out that I didn't print them out. It's a lot. So this goes to show that, what they look like in the output here. And I copy all of them into a table. Forgive me, this is from a different paper, so I use different algebraic symbols to indicate the random effect coefficient. Just know the cohort here correspond to our C0J, where J goes from 1 to 17, and then the period is actually our P0K, where K goes from 1 to 9. So this is the output for the random coefficient estimate. You don't care about that much about the p-value or the test of each individual coefficient. They don't tell you much. You care about, just as in the linear model case, you care about the trends within each classification of period and cohort as a whole. So the way I like to do this exercise is to visualize the effect that I just estimated to see the trends more clearly. I plot these coefficients, and translated these log coefficients into a probability to see more clearly the period trends, because period change is the one that we estimate to be statistically significant. So we focus on the period trends of obesity here. We can plot the estimated coefficients out where the blue line, so the y-axis is the predicted probability of being obese with the 95% confidence interval. The blue line, what does the blue line mean? Anybody can take a guess? Where does the blue line come from? Right, it may not be obvious here. This blue line means it comes from the estimate of the adjusted mean. The logic coefficient gamma 0 being negative 5.56 and translating into probability of about 0.36. So on average, the US population over this time period had an estimated probability of obesity of 36%. Okay, so this is what this line means. So as you can see, the period random effect shows up as a deviation from this adjusted mean for each period. right? So the calculation goes beta 0K, which is the period obesity effect, is gamma 0, this adjusted mean, plus P0K, which is the period random effect coefficient. You get this from the previous table of estimate, and then you translate them into probability and put on the graph. Right, so what you see here is a pretty remarkable trend of obesity epidemic in the US, where we see large increases over time from only 20% all the way to over 40% from 1970 to 2000 and continuing on into early 2000. Paul? Mm-hmm.
If you want me to do the earlier one, wait on it, but.
You can do it right here, not over here.
Okay, so the more topical one to this graph, in this graph, how do we get the confidence bounds? Do you have code that would do that?
The solution from this, the output here, the point estimate and standard error, that gives you the interval estimate. It directly comes from the output. And there's another question from earlier.
Yeah, the earlier question is a more theoretical question back to the model specification. And this person's asking, does the hierarchical formulation assume the P and C random intercepts to be independent of controlled regressors, just like in standard random effects models? Let me know if you need me to repeat that. It's a little bit dense.
Yeah, I think I got it. It does have the usual assumption of the mixed effects models. Yes.
And then the follow-up to that is then if that's true, what you just said, how plausible is it? How plausible is this assumption in the context of APC applications? So like, do we believe this is really we're gonna meet this assumption in real life or not?
There's no direct test of independence, which is by the construction of the model. And then I think what's critical is the theories behind the specification of the model, where we conceptualize period and cohort to be at a higher level where individuals nested. And therefore, so they're assumed to be an independent source of errors compared to the individual level errors. So I think that's, in general, that applies to all individual level covariates. With regard to age, that can be also tested. I think I've done some experiments by, we'll talk about this in the random coefficient part of the model, where you also test for the random variation of the age coefficients across cohorts and periods. They often turn out to be not significant, which has been the case for the obesity exercise. So that's another way to test the independence of assumption. I have not encountered that the problems of that because of the benefit of the mixed effects models, where the relationship between period and cohort and age with Y, with the outcome, are not assumed to be linear. So that is the critical part that moves beyond the usual independence if we were to put them in the model linearly as three regressors simultaneously. So good question. We have another one.
For the cohort variable is correlated with other predictors like location or income, why not we put it as a empirical variable in the model?
When the cohort effect could be correlated with education or income at an individual level, what is the second part?
Just put it in the model as a empirical variable. Give it the random percent.
Oh, you mean why do we put them only in the individual level model, but not also at level?
I mean that we can put the cohort variable as a categorical variable in the model rather than
categorical. It is categorical by nature, but it's at level 2.
So only on the level 1, we can include it as a categorical variable, right?
Right. The whole point of the mixed effects model is to avoid the specification of linear cohort and period variable to be as fixed effects in this equation. I get at some of I will show next in the random and the level 2 covariates where it's also in the book chapter where we also specify cohort level education, period level education. So education. So some individual level covariates here can also be used to construct level 2 covariates to measure the level 2, variance, and that can also be done and has been done using the cancer as an example in the book. But I don't have time to show you here, but it's quite flexible that you can also specify these covariates at either level or both levels to test for, to account for some of the variance in that variable cohort or period. But the reason why I don't include period and cohort as categorical or continuous doesn't matter variable in level 1 is the whole point of avoiding the specification of linear relationship between cohort and period with the outcome at the same level with age. Great questions.
There's a couple more just following on this topic. So this means, for instance, if you controlled for education in the fixed effects part of the model, if you estimate cohort effects, will they be uncorrelated with education by design? That's one question. And then if you estimate the BLUP of cohort, they must be uncorrelated with education. I'm not sure if that's making sense, but
yeah, I think I get it. Yes, that's the assumption. That's the assumption. And whether or not it's a tenable assumption, it's an empirical one that one needs to test. Yeah.
And then one last one back to this graph. Do you have a comparable figure for the cohort effect?
I do not. I do. I don't show it here because here again, it's a great question. I like to emphasize. We have already just tested the cohort variance not to be statistically significant. So I did not separately show a cohort effect, so it will be pretty much flat. But it goes on further. I think I'm running out of time. I'm a little nervous, but let me just try to zoom in on. So
Sure,
based on what we have done, I'm going to come back to those questions because I think it's that's why I think it's important to run through the slides. Building on the basic specification of the random intercept, we could further specify random coefficient, where level 1, attributes or characteristics can also be assumed to have level 2 variance, such as sex and race, age as well. I did not include age as random coefficient here because of preliminary analysis that have shown that they are not significant. And also education and income. So here I focus on sex and race, and they answer the specific question of whether the sex-race disparities in obesity also vary by time period or birth cohort. And so therefore at level 2, in addition to the intercept, we have also the random components for sex effect and race effect, right? So you can do a quick dribble if you have time to see, want to figure out what the combined model looks like. Should be pretty straightforward. And if you think it looks like this, you're correct. So again, the fixed effects part are the same, where we have a more expanded random effects part that correspond to the random effects for both sex and race. And here are the interpretations of these different model coefficients, kind of readily available, translatable based on our first part of the example. So here's the SAS code, where everything else is the same except for the random statement, where you add not just the intercept but also sex and race into the random statements here. And here are the updated results. On the top is the fixed effects, which are largely similar as before. What's expanded is the variance components part, where we have estimates for the random effects by cohort for sex and race, and also period effects for sex and race, where we find, particularly for race, we have significant cohort variation. So quickly, if I just put them on the graph, this goes back to the last question, Paul, that you read out, where this is the plot of cohort trends of obesity. Then I I did not show earlier on because earlier on is the overall cohort effect that did not show up to be significant. But here, it's interesting to inspect the racial gaps in obesity, which turn out to be to have significant cohort variation, where you see this is white, this is black, this is white from females and males prior to in the former example where there should be a flat line compared to the upward trend of period line. This is so this part is directly comes from there that it corresponds to the reference group. The reference group is white females. As you can see, it's pretty flat, right? But for their black counterpart, it's not flat. And particularly, there's a big uptake for cohorts born after 1970, where the peak obesity probability is 50%. So across the cohorts, the racial gaps increased significantly for both females and males, based on, mostly contributed by more recent cohorts of blacks. And so, I gave a little bit of detail here for how to calculate all these numbers on the graph, where you, like I say, this is for black female, and you add up all the cohort random coefficient for black male. If you omit the sex and race part, that's the reference group for white female, which is this line. And then all the other three can be calculated similarly according to this specification. So this is something much more interesting than before that you can investigate with random coefficient model applied to the obesity to look at sex and race changes over time. And then another extension is the adding the level 2 covariates. Here, an example that I showed is from the general social survey data on happiness, where the random intercept model can be specified by looking at the basic question of, do people get happier with age and over time? Are there any birth cohort differences in happiness? Whereas random coefficient model can help us address the question, how do social inequalities, such as sex, race, and educational difference in happiness vary over the life course and by time? And adding level 2 covariates can further help us to address what period and cohort mechanisms may have contributed to these differences and changes. So I have to move like 5,000 miles per minute speed, but this again should look familiar because it's a similar sort of level 1 within cell model that specifies individual level characteristics, age, sex, race, education, and other X factors that are related to happiness for the set of data. It has exactly the same data structure as Ainhain's obesity across 22 surveys. And at level 2, this is the familiar random coefficient model where we look at what overall mean. It has both period and cohort components. But for sex and race, we focus on the period changes in sex and race effect. The model estimated age effects. In the J shape does show happiness increases with age. I think this is the single most important slide of all the lecture, that we all have something to look forward to. And this is the period specific trends by sex and race, which show a lot of changes over time for sex and race. And then so this is the sort of the target of the next stage of modeling. We're trying to explain this. There's some cohort differences as well, which I'll show next. So here the exercise is that I want to know what's going on, what's underlying the observed trends, for different groups of the population by sex and race over time. So we could do this based on previous research and literature review that suggests that money and happiness seems to be related. So this goes to the exploration of some macroeconomic conditions such as employment rate or GDP per capita, and I want to see how they may map onto the period trends in happiness. So on the top is the percentage of being very happy in the population. And then on the bottom, the green line indicates unemployment rate over time, and the pink line indicates change in GDP. There's some sort of correspondence in temporal trends of happiness in these variables, so we might want to test them. This is a very interesting graph where on the top is the cohort trends in percent very happy. Everything's kind of flat except for this dip that corresponds almost perfectly to the baby boomers. So the lower blue line is the relative cohort size. So the larger, the bump here corresponds to the baby boomer generation, 1946 to 1964. So the larger the cohort size, the less happy they are. There seems to be some interesting to explore. So in order to test these hypotheses of level 2 covariates that may contribute to the period and cohort trends, we add these variables to the overall mean model, as well as the period changes in sex effect at the macroeconomic variable, and then the race variable. RCS here indicates relative cohort size. Sorry for the abbreviation here, to explain the overall cohort trend. And so I skipped the combined model, but here's the results. So the panel A here shows the model results without these variables in. It's just the intercept, sex, and race, and the variance components for period and cohort effects, right? And so model B here adds these, employment rate, change, GDP, and relative cohort size to the intercept model, and then the macroeconomic variables, employment rate and GDP, into the sex and race model. So the fixed effects estimates show that higher GDPs is related to more people being happy. Relative cohort size is negatively related with happiness as expected, and GDP also seems to be related to smaller sex gaps in happiness, and also smaller race gaps. Small numbers, I apologize. Smaller race gaps as well. So good economy, less inequality. And then, so the most important part of the analysis by adding the level 2 covariates is that by adding them, you need to, the evidence of them working is that if you observe any percentage reduction of the various components compared to the models without these covariates. So for the intercept, unfortunately, these variables don't explain much. But for sex and race effect, the GDP explain away 83% of the variance in sex effect, although the sex effect is not significant to begin with. But it also explains about 40% of the race gaps in happiness over time. And relative cohort size explains 73% of cohort variation in happiness, that single variable. So so these are kind of additional, more complicated analysis you could do by adding level 2 covariates. And then in the example, I'll just reiterate because it related to a question earlier, that in additional examples that I gave in the book, where we used the same CCREM analysis to aggregate cancer rates data when the time intervals of those race data are not equal. So they can be sort of the similar kind of data structure as research design 2. In that example, we did also show cohort level education, cohort level health behaviors such as smoking to be related on top of individual level education and individual level smoking to explain cohort-specific and period-specific variance in the model. So I encourage you to go to the corresponding chapter to look for additional details. Another extension is that one can do Bayesian inference for small sample problem, at level 2, meaning when you have fewer time periods and fewer, birth cohorts. Here in these examples, I have huge numbers, 18, 22. What do you do when you have smaller data? So there's, example using Bayesian inference as different from frequentist assumption that can, better estimate the problem. And then also you could expand here what we do is between group inequality problems, so between, sex and race, different education. One can also apply this in conjunction with variance component regression to look also within group heterogeneity problem, and there's an example of that. Further, one can conduct F-test, which is the most exact test for level 2 variance components, especially when the sample size at level 2, the number of P's, the number of C's are small. F-test is preferred to Z-test. That can give you a better test of the significance of period and cohort effects. I will just wrap up by sort of a general comments about, where we are. So we talked about linear models, and this is the mixed model. So why do we consider this the second one? So there are a number of advantages. I hope I've made it a bit clear through today's examples that they have over the linear APC models. Is that first and foremost, it offers a much more flexible modeling framework and allows us to do a broader range of substantive research, particularly as it relates to variables beyond age, period, and cohort. And thus, it can allow us to do deeper investigations of potential explanatory mechanisms and move us beyond identification problem and accounting models. And here are the key references in case you're interested in looking into this further. I have omitted a gazillion methodological details due to the time constraint, but these articles do a good job of covering all the territories. So I'd stop here, and how we're doing in time. Okay, we have. Yeah, we're almost close to the start of the next section, but let's do another 5-minute break. If you need more, let me know. If you 10 is better. 10 or 5. Okay. Oh, yeah. Yeah, you guys are free to move, but I will see what questions that they have, Paul.
One's more complicated. The simpler one is about, do you have a recommendation for a minimum number of clusters, P's and C's, for the hierarchical specification to be viable?
That's a great question. There's no textbook classic of the minimum. Based on my experience and the rationale for inference of, based on Z, for example, I think there should be at least 5 for it to make sense. If you have less than, just a few, 2, 3, 4, the best thing to do is to estimate fixed effects, indicator variables, quicker mean, as dummy variables, and you also will need to address the, so in that way, you can estimate a model with reasonable estimates for fixed effects. The only thing that's missing that cannot be tested would be the clustering of those individuals within each level 2 unit. But computationally, I think that's, what's feasible. I would say at least 5.
And then, sorry, James, I'm going to skip yours again. It's a little bit complicated, but let me just knock out these simpler ones. So when adding level 2 contextual variables to do mechanism testing relevant to P or C, all P or C related level 2 variables are collinear to each other. Does this matter for model estimation?
When the level 2 covariates are correlated with each other, and I think it shares the problem with collinear regressors 1 of. So there would be not resolvable.
Okay. And then we've got James asking he says, got a question with the variance components model. Would it be okay to come off mute to ask later? And then he's got an earlier one in writing, which is a follow-up on stuff that you had talked about earlier. So, I don't know if you want to have him come off mute right now during the break, or whether you want to just handle this at the end or do it offline. It's up to you. I mean, if you need a break, feel free to. I know we haven't given you a chance to take a break.
Maybe toward the end.
Okay.
Yeah, I just think that, it's a good
Sure.
time to break.
So yeah, James, we'll try to get to yours probably at the very end, I would guess. And then if we, if given time, and then if not, we'll make sure that you've got a way to raise this offline.
Thank you, Paul.
Thank you.
So I turned on the ceiling light.
Sorry, I keep forgetting.
You want to use this or?
Yeah, I can do it if it's better.
It's
Yeah.
probably better, but yeah, if you don't remember, I'll just.
Sure, thank you. I'll try to be quiet when I'm not actually talking.
It's okay, it's turned off, and so that's off right now. I'll mute.